Okay, so all you had was the letter M and theta. Then you could express your final answers in terms of those, M and theta, and G, which is of course a known constant, right? So that when the number delivery truck finally arrived, you'd have done everything you possibly could have to set up your answer. And all you'd have to do is throw your numbers in then. And if the number delivery truck arrived and it actually had 17 different sets of those numbers, you just plug them in 17 different times to the expressions you've already prepared. Okay? This is how we're going to increasingly move to doing our solutions. It's more powerful, your answer is more general, and we'll find, in addition, we have access to error checking in our answers that we would not have access to otherwise. Okay? So the number delivery truck is going to start running late and then not arriving at all. And the rules of the game are that you can only express your answer in terms of given variables and known constants. The reason why is if you could just make up your own variables, it'd be anarchy, right? T1 equals smiley face. What's smiley face? The right answer. Okay, you can't do that. Now, as ridiculous as that seems, I see this all the time. You see stuff like this. T1 equals mg minus smiley face over, x squared q, and it's got a lot of stuff in it that's given, but then it's got something that's forbidden. Well, what's smiley face? Smiley face is whatever the right number that when mg minus smiley face over x squared q, it gives you the right answer. You can see it's the same problem, right? You can't make up your own stuff and leave it in the answer. And the reason why you might have your own made-up stuff is because sometimes it's necessary to introduce your own variables because you can't progress in the problem at all. And if you don't do that, you need those things to fully describe the situation. The thing is, though, to clean up after yourself. If you want to introduce something to feel like you make progress, make sure you drop it out at the end. Okay? Make sure it's gone from your final expression. Okay? So generally speaking, there will be givens, check marks, that includes known constants. There will be asked, things that you are looking for. And then you will also have a third class of variables, which is needed for progress, but they cannot appear in your answer. So get them out by the end. Okay? This is not one of those problems, but we'll see those coming up. Okay, are there any questions on symbolic solutions before I move forward? All right, so I said that I would informally talk through the problem-solving strategy during this problem. Now let's write it down and formalize it. This is your recipe for most, if not all, of the problems on your homework number 4 and 5. This is the force problem-solving strategy. You want to walk this like it was a tightrope, because you can really get off track if you don't follow it carefully and think that you are at a dead end. Step 1. You want to identify your object of interest. You want to pick the object, and that's the things you're going to be looking at forces on. Okay? There are sometimes problems with 3 or 4 different objects, and you need to pick one to focus on as your interest and ignore the others. You're basically cleaving it into the whole situation into object, and everything else is environment. Okay? So I did that here. Okay? Notice I did that. I picked my sign. My sign is the thing that I cleaved in as my object, and everything else was the environment. Okay? There are other forces here. In fact, every single one of these forces is 1/2 of an action-reaction pair, with the other half acting on something else. So for instance, if the mass gets pulled down, what's get pulled up? What's that? What's the action-reaction pair to the force of gravity? The force of gravity that pulls up on the Earth, right? We talked about that one last time. I don't care about the Earth in this problem, though. I care about the sign. What's the action-reaction pair to this tension? Well, the tension, of course, the rope itself can't do anything. If there was nothing on the other end of the rope, it would fall down. The rope is just a way to transmit force from the wall. So there is also an action-reaction pair that way. So the wall gets pulled to the right, and in exchange, the mass gets pulled to the left. Okay? We can draw an action-reaction pair to this tension too. So this, the sign gets pulled up and right, and in exchange, the ceiling gets pulled down and left. Remember what we're doing in Newton's second law. We're looking at halves of action-reaction pairs. Every one of the forces on the sign has a reaction somewhere else, but we don't care. That's the idea of IDing the object of interest. We're gathering up halves of action-reaction pairs on this object. So the next step is to identify forces on this object from the environment. So we've cleaved off object from environment, and now we're interested in how the object affects this, or how the environment affects this object. And when you're identifying these forces, of course, you want to use your rules of thumb to figure out which ones would be relevant. If you're on Earth, probably include the force of gravity. Gravity doesn't turn off. And don't include the tension if there's no string attached to your object. You don't include the tension because the tension's on its own work. Okay? You include the tension when there's a rope attached to the object. Okay? Okay? Then what you do? Well, you probably at this point have a bunch of forces identified acting in potentially a bunch of different directions, and you need to bring order to this chaos. So what you're going to do is choose your x and y axes. So that you can resolve all these pushes and pulls into tugs of war on these coordinate axes, and you can think of them independently. So how do you choose your x and y axes? I chose the good old standard x and y axes here, and that's not because that's what you always choose. It's actually a good decision in this problem. It would be a terrible decision in other problems. So while it wasn't super relevant to my first example, I want to tell you a little bit about how to make this decision. If the acceleration is 0, which of course it was in my case, or its direction is unknown, all you have to do is pick your axes to minimize your components. So if your acceleration is 0 entirely, or it has some acceleration, but you're not exactly sure which direction it is, all you want to do is pick it to make your life easier. You want to pick your axes to minimize the amount of components that you have to deal with. So you don't have to do this SOHCAHTOA all day. So look at my situation, right? I had 1, 2, 3 forces, but I picked my axes like this, not because that's what I always pick. I picked it because then this is entirely a minus y component. This force is entirely minus x, and I only had to do SOHCAHTOA on one of the 3 forces, right? If you pick some other axes, so you have to break all of the forces in the components, that seems like more work to do than you need to do, right? However, if the direction of the acceleration is known, what you want to do is you want to pick one axis along it. This will make your life a lot easier. Let me give you a brief example, just in the abstract here. Let's say I somehow knew that my acceleration was in that direction. What you would do, if the object had an acceleration in that direction, you'd pick one of your axes to go along with it, and the other one would be like that. Now, what's the advantage of that? Well, what that means is that the acceleration is entirely in one direction and not at all in the other. Okay? So you have effectively, instead of having to tussle with both components of the acceleration, one of them will automatically be 0 simply because you chose it that way. You chose the acceleration to be entirely along one axis and has none on the other. Okay? Okay? So as far as choosing your axes, obviously some of the problems we'll do in the future will we'll get into what are these choices, why we would make certain choices. But this will lead us to some very strange axis choices, something diagonal things like this. So if you go on that vector practice PDF worksheet that I posted for you guys, it's under the Math Skills Review. There are some really bizarre looking axes that I've asked you to resolve components to, and that is not just to torture you. We have good reason why we want to do that. What do you do next? Well, now you're going to so you're going to break your forces into components along those axes. So you're going to break your forces into comps. Now that you've chosen your axes, you can break into components along those axes. And at this stage, I strongly advise you, until you get really, really comfortable with it, to draw a free body diagram. Draw a free body diagram. Basically, if you draw a good one, you can basically read off it what your equations are going to give you. I suggest doing this after you put in the components, because then you can think of it as tug of wars along the x and y axes independently. Okay, so the free body diagram around here after you've done the components. And then you basically put into your master equations. Your master equations, as we've mentioned already, f net x is equal to f1x plus f2x plus however many you have, leading to any x acceleration if there's any net force left over in the x direction, if everything hasn't killed each other. And same thing in the y direction. The net force in the y direction comes from the competition between all the y components. If they don't kill each other and there's something left over, that's what leads to acceleration in the y direction. Now at this point, what you have is two equations, and now it just becomes a math problem. I guess I'll put this over here. So you can solve for up to two unknowns. They might not always ask you for two, but two is the maximum number because you have two equations. And this could really be anything, okay? It's anything involved. So it's not just they give you the forces, ask for the AX and AY. Sometimes they give you AX and AY, like in the sine problem. We knew that there was no acceleration in either direction, right? Now we work backwards to find T1 and T2. I could have given you T1, but asked you for T2 and theta. Just pick your two favorite variables. You can solve for them. It doesn't matter. Once you have two equations, you can isolate any two ingredients. So this problem could have been phrased in many different ways. I could have given you T2 and T1 and asked for m and theta. It doesn't matter, okay? So don't be too beholden to any particular thing. Just write down the equations, and you'll find there's two things missing, and you'll get them, okay? You can solve for them as long as you have no more than two things missing out of two equations. Okay, so that's the strategy. You can hopefully see that we did do the recipe steps 1 through 6 in the example that I did. And I will be much more carefully saying step 1, step 2, step 3, step 4, step 5, step 6 as I go through subsequent examples, and you'll see the recipe works. All right. Are there any questions before I go to another example? Okay. So before I start another example, I guess let me stir one more force into the pot, the support force or normal force that I've been mentioning. So one more force, the normal force. This is the support force from a solid surface. Again, this is not a force to include in every problem. It's a force to include if your object of interest is touching a solid surface. Otherwise, you have no need for it. So these are just giving you tools to apply when relevant. As with any force, we want to discuss rules of thumb for the size and direction so that we can think through them in a particular situation. Before I do that, I guess I should tell you my notation. I'll use n vector for normal force. When I want to refer to just the size, I'll write it like that. I know this is confusing, so we'll have seemingly strange statements like this, n equals 10n, which looks like mathematical gibberish, until you realize this is n as a variable, meaning size of the normal force, and this is n as a unit, meaning newtons. Okay? So this statement is just using the capital letter N in several different ways. It's saying the size of the normal force is 10 newtons. It's, by the way, not the first time we've double used a letter, so it's going to happen. We have to give ourselves up to that. We've actually had 3 different usages of the lowercase m so far. M as a variable is what? Mass. But m as a unit is meters, and m as a prefix is milli. Okay? So there's only so many letters. You have to get used to double usage. It's no accident, by the way, that I'm moving forward to doing symbolic solutions. So I'm kind of bringing in the variables while the units and numbers kind of phase their way out. Okay? So that hopefully won't be too confusing. All right? So let's talk about rule of thumb for this. So here's a solid surface. So why don't I go through the table? Of course, if I'm pushing down on it, it pushes up. But up is not a great way to say it. That just happens to be because the surface is horizontal. So for instance, if it were tilted, I could push into it, it would push back, right? Now it allows me to move parallel to it. There's friction, but that's a different story. But when you try to go perpendicularly into it, that's where the stuff is, and it doesn't want to let you go in there, so it pushes perpendicularly away. So the direction is perpendicularly away from the surface. By the way, that's where it gets its name, normal force, because normal is another word for perpendicular. It's not always up. In fact, if I push on a wall, the reason I don't go through the wall is because it pushes horizontally back. Okay? So the normal force can be vertical, it can be horizontal, it can be diagonal. It's just perpendicularly away from the surface. Now, how much is it? Well, it depends. The whole point of this is an ad hoc constraint to make sure you don't smush your surfaces in a problem. So you don't have your objects accidentally going into a surface where it's not allowed to go. And so the size varies, but basically it protects the structural integrity of the surface. So obviously at some point surfaces break. If I push the table hard enough, I'll break it. But neglecting that, we're going to assume basically that the normal force is whatever it needs to be to prevent the surface from getting smushed. Okay? So it is there simply to protect the structural integrity of things so that when you have a motion of a body, it doesn't go somewhere in where it's forbidden to go. So to give you some examples, let's say we have a horizontal surface. If we have a horizontal surface, one of the things that threatens to pull an object into the forbidden zone there is, of course, the force of gravity. So in this case, the normal force says nope, and it kills it. So in this case, the normal force is equal to the force of gravity, or mg. If I put a heavier object, we learn that the force of gravity is larger. And of course, the normal force, we need to kill that. And to the extent that the surface doesn't break, it must. Now, I'm sad to report that that statement right there becomes a knee-jerk thing that people write down for the normal force in every situation, even when it's very, very not applicable. So don't let your understanding of normal force begin and end there. And to try to nip that in the bud, I'm going to right away give you an example of something else. So let's suppose I have an object on a surface, and not only is the force of gravity trying to make it accelerate downward, but I additionally push downward on it. I'll have a pushing force. So it's like this. I have the force of gravity pulls it down, and I'm going to push on it too. Well, now, in order to protect the structural integrity of the surface, the normal force has a lot to do. So here, the normal force is going to have to kill both of these. Right? So it has to be equal to their sum. If the job of the normal force is to protect the structural integrity of the surface, now it has two forces to fight, and therefore, of course, must be as big as both of them combined. So make sure you understand here the normal force is greater than the force of gravity, because the normal force has to do double duty here. I could have the opposite. I could have that I lift some small part of the weight up, right? Not the whole thing, but if this thing weighs 10 newtons, maybe I pull up 2 newtons, right? So if that's the case, the normal force doesn't have to do as much, right? So if I have the force of gravity is 8 newtons, but I pull, 10 newtons, but I pull up with 2 newtons, how much does the normal force have to do to protect the surface now? It has to cancel off the other 8, right? So here the normal force is less than the force of gravity. It just does what it needs to do. If it needs to cancel off gravity, it'll do that. If it needs to cancel off more than the force of gravity, it'll do that. If it doesn't have to do as much, it won't. It's just whatever balances out the situation to make sure you have no motion into the forbidden zone where we have a solid surface where the object can't go. We assume that the surface is able to supply the force to make sure you don't go in there. That's the nature of the normal force. Have any questions on that? Okay, so let's knock off there. I'll start doing examples with the problem-solving strategy next time, folding in the normal force.